Hello, my name is Peter McMahon. I'm the Technical Sales Director for European Industrial Chillers. We are a specialist supplier of water chillers for air conditioning and process cooling applications. However, we would also sell a lot of HVAC equipment such as air handling units, close control units, fan coil units and heat recovery units. I'm very regularly asked what is the latest and greatest in relation to new technologies, innovations and so on by consulting engineers that we deal with on a regular basis. As a representative for AirMech in Ireland, we are continuously hearing of really good products that are coming out from the R&D factory or the R&D department in the factory. So as a consequence, I've decided to start doing a couple of video blogs, brief presentations on various products that are coming out. I have historically drafted technical bulletins, which you can see on our website, eicl.ie, and go into the services section and you'll find it there. But I'll do a couple of videos, see how we get on. If the feedback is good, I'll keep doing them and we'll go from there. So today I'm going to explain about the MultiChiller sequence controller. This is one of the really good products that's come out recently. Unlike historically where you would have maybe 2 or more chillers in a system, the first chiller would typically be run and then maybe you would have a duty assist or duty standby with the other chiller, and you would time to change them over at some stage unless there's a fault. If there was a fault, you get a signal typically back to the BMS that would bring on the other chiller. However, the problem with this design concept is that there's little or no regard for the part load efficiency. If you run the vast majority of chillers up to 100% load, they're running at their least efficient mode of operation. So if we pay consideration to the part load efficiencies, you can see how we can dramatically improve the efficiency of a system. So that's what this is all about, so I'll crack on. Just to make the point, if you look at a catalogue, pretty much any chiller manufacturer's catalogue or product guide, you will see they'll give you the cooling capacity for whatever model. So for example here, this is an AirMech NRL range. They would have a standard low noise, high efficiency or high efficiency low noise. We have the corresponding input power. So for example, if you divide your cooling capacity by your input power, you will have an EER, your energy efficiency ratio. There is also a formula ESEER, which is much more relevant because your EER, like I said, is only relating to when you're running at 100% load. And chillers are typically sized to operate at the hottest day of the year, solar heat, bodies in the building, lighting and so on, and they rarely ever run at 100% load. So the ESER is a much more realistic figure. It's a calculation, it's a Eurovent approved calculation. So it's based upon looking at the efficiency of the chiller at 100% load at an ambient of 35 degrees C, and it's a weighted formula, so that means it assumes it's only going to run at 100% load for 3% of the year. And it goes on down. At 75% load, it would be at a lower ambient and it would run at a much higher percentage, in this case 33%, and so on and so on. So when we input all this data into the formula, we will have a figure for the ESEER, and that's a much more realistic assessment of the energy of the unit. So different types of compressors would have different performance characteristics. So for example, this would be a scroll type, this would be a screw, and you can have a non-inverter and an inverter type screw, by the way. The non-inverter simply means the rotor runs at the same speed and they would typically recirculate the refrigerant with a slide valve or something like that. And then of course you would have a turbo core as an option. There used to be also piston reciprocating compressors, but they're pretty much obsolete now in chiller manufacturing. So I just want to give you an example of a couple of part load efficiency curves. So you can see various different ambients here. In Ireland we use a design ambient of about 27 degrees C. Typically the hottest day of the year in Ireland is typically considered to be, I think it's 26.6 on ASHRAE, I think. So if we look at the ambient at 26 degrees C and we follow it up here, we can see the efficiency of the scroll chiller in part and low load is consistently improving almost down to about 20%. We can compare this with the screw compressor. So this is the non-inverter screw compressor first of all. So you can see the efficiency goes up as well. It seems to drop off a little bit, level off, and then drops off at the end. But again, in general, the efficiency is better in part load than up at 100%. Again, we can compare this with the inverter screw. And you'll see the inverter screw has an improving efficiency almost consistently in part and low load. So obviously that's a really good option, especially for an application where you expect to be running in low load. The turbo core, finally, is far superior in part and low load. Consequently, it's a lot more expensive as well. And you would need to make sure you have, if you're buying a turbo core chiller, you buy it off a company that have a good after sales service, because it's very specialized equipment. And you pretty much need a laptop to plug in to analyze what's going on with the turbo core machines, but a good option. Okay, so this is kind of an overlap. I have another example here. Sorry, let me just get rid of that. You can see this is live because Facebook is jumping up here. Okay, so you can see an overlap here where we have our scroll. The scroll is the NRB. I think this is color coded, yes. So the NRB is the blue. The turbo core you'll see is the best. We have the NSM, which is the non-inverter screw, which is this one dotted here, and the inverter screw. So you can see how they overlap. But in general, the part load efficiency is better on the vast majority of them. So when we know that the part load efficiency is better, there's no sense really in running a chiller up to full load. We're better off running a multiple of chillers in part load. So ERMIC designed what was called the MultiChiller sequence controller, and unlike the BMS historically giving an enable signal to each chiller, and like I said, it would run one, then if it needs the other, it would run that, but it wouldn't be anywhere near as intelligent as the MultiChiller sequence controller. This is programmed specifically to suit the type of chillers and the type of compressors in the chillers. So whether it be a scroll, inverter screw, non-inverter screw, and so on. And it understands, let's say when you have a scroll chiller and it's getting up to 70% load, and we know the efficiency is dropping off, it will then decide to enable the second chiller and run the two of them at, say, 35%. So instead of having an EER dropping off to 3, you might have 2 chillers running with an EER of 4. So obviously it's far better to do it that way. So this is simply how you would have your system. Chillers connected in parallel. Obviously you need to run the pump for the chiller that's on. So you would have an additional flow rate when you enable that chiller, but you might have a couple of kilowatts of a pump. But if you consider you have chillers with a couple of 100 kilowatts of absorbed power, you can see the efficiency is quite good. You need to locate a temperature probe on the common inlet, common outlet, because you're now analysing the system load. And obviously as the return temperature increases, you have a higher delta T, the MultiChiller controller realises the load is increasing and interprets the load, and consequently enables the chillers as required. Okay, that's just an example of the screen you would have. That's the older type. This is the newer type now. It can interface with pretty much any type of ERMIC chiller that we would have in the range. Applications, everything. Across the board, data centers, telecommunication, like I said, across the board. If I mentioned earlier, I previously used to do technical bulletins. Again, if you want to go onto our website, you'll see the link, eicl.ie/technical bulletins, and you can have a look at all those. Technical focus number 9 is a little analysis where I've compared, I think it was a 550 kilowatt system, 550 kilowatt chiller, 2 of them, and with the absorbed power for the pump. And it's just an example of how you would understand the energy savings there. In addition, there are some really good videos again on our website. On the home page, go down to the bottom and you'll see a link to some of the ERMIC videos that we have there. ERMIC do have their own channel. If you just Google ERMIC on YouTube, you'll see that. That's it. If you found it useful, please give me some feedback. Let me know. Subscribe. It's a new thing I'm doing, so any feedback would be good. And I'll keep going if it's positive. Okay, thank you.